As we start exploring the calculus of multivariable functions, we first need to understand the idea of a limit of a two-variable function. Just as limits for single variable functions tell us how that function behaves near a certain point, limits for a multivariable function are going to tell us how a surface behaves near a point. We'll see that they are foundational for understanding ideas of partial derivatives and continuity, but we'll also see that unlike single variable limits, where we only need to consider the limit from the left and the limit from the right, when dealing with functions with multiple variables, we're going to have to consider the approach from several directions. The bottom line is that in two variables, we can approach a point along infinitely many paths, and our approach to limits is going to have to take that into account. Recall that in single variable calculus, when we say that the limit as x approaches a of f of x equals L, what we mean is that as x gets closer and closer to a, f of x is getting closer and closer to L. There's only two directions, from the left and from the right. And for that limit to exist, the limit as x approaches a from the right of f of x has to equal the limit as x approaches a from the left of f of x, and both of them have to equal L. In order to understand limits in two variables, we're going to start with a very formal definition. So if we have a function f of xy that's defined near some point AB, then we're going to say that the limit as x and y approach AB of f of xy equals L if, for every epsilon greater than 0, there exists a delta greater than 0, such that the distance between xy and AB is less than delta, implies that the distance between f of xy and L is less than epsilon. There's a lot to unpack in that definition. However, we can interpret it as saying that when xy gets close to AB, then the function value gets close to L, and the function value gets close to the same value of L regardless of the path by which we approach our point AB. If we think about this geometrically, what we're considering is that as the point xy approaches AB in the plane, in other words, as we travel along some path that moves towards AB, our function value approaches L in 3D space, which means our surface is leveling off at a height of L. If the surface approaches different heights along different paths, then we'll know that our limit doesn't exist. Let's look at a few images to understand these differences. Here we can see that as we move towards the xy point 0, 0, our z values are all moving towards the pinnacle of the surface. This would be true regardless of the path that we took across that surface. Let's compare that to what happens on this surface as we approach 0, 0. Notice that if we approach xy equals 0, 0 along the line y equals 0, the green line in the diagram, we see that the limit would be the z value of 1. However, if we instead approach it along the line x equals 0, the blue line in the image, we see that our limit is negative 1. So while the limit as xy approaches 0, 0 on the left does exist, the limit on the right does not. When limits of two variable functions do exist, they abide by many of the same laws that we saw for limits of one variable functions. In particular, if we have a function f whose limit as xy approaches ab is L, and another function g whose limit as xy approaches ab is m, then when we add the functions f and g together, or we subtract them, we can add or subtract their limits. When we multiply f and g, we can multiply their limits. If we multiply either function by some constant c, we can multiply the limit by the same constant. If we take a quotient of the two functions, then the limit of the quotient is the quotient of the limits, provided that the limit in the denominator is not 0. Similarly, we can take the limit as xy approaches ab of the function raised to the nth power and raise the limit to the nth power. And if we take the nth root of our function, we can also take the nth root of our limit, assuming that limit is positive when n is an even number. So with those in mind, let's think about how we might actually evaluate limits. Generally, we'll start with direct substitution. We might need to do some algebraic simplification. If that doesn't get us to an answer, we might try applying some limit laws. If it looks like we're going to run into trouble, then we have to start investigating different paths to see if we might be getting different limits. While substitution can be a useful tool, we never get to assume that just because it works in one direction, it's going to work in every direction. Let's start with a pretty straightforward example. Here you want to evaluate the limit as x of y approaches the point 2, 1 in the function 3x squared minus 4xy plus y squared. This is a polynomial. We know that its domain is the entire Cartesian plane. There's no values of x and y. We can't plug into that. And just like for single variable functions, for polynomials, the limits can be done just by straight substitution. So this limit is going to be given by 3 times our x value squared minus 4 times our x value times our y value plus our y value squared. So we get 12 minus 8 plus 1, which is 5. In our next example, we see that we've got a quotient, so we're approaching 0, 0. And we want to see what this limit is. And we know that we can use the quotient rule, the limit law about quotients, which tells us that we can take the limit of f over g is going to equal the limit of f over the limit of g, as long as this denominator is not 0. And since our top and our bottom are once again polynomials, we know that we can evaluate the individual limits just by substitution. So if we do that, on the top we get 0 plus 0, which is 0. On the bottom we get 1 plus 0 plus 0, which is 1. And so when we take the ratio of those limits, we get 0, which means that our limit value is in fact 0. All right, we're going to ramp up the complexity a little bit in this last example. We're going to be examining the limit as xy approaches 0 of a piecewise function that's defined as x squared y over x squared plus y squared when we're not at 0, and 0 when we're at 0. So we might have some sense that this limit is actually equal to 0, which would make this function continuous. We'll talk about that idea a little more thoroughly in the next video. But we have to remember that if the limit of the absolute value of f approaches 0, then it's also going to be the case that f itself is going to approach 0. And that's going to be an important idea here, because what we want to do is we actually want to look at the absolute value of our expression. Remember that we can't look at the function value when we're at 0, 0, we have to look at it near 0, 0, which is why we have to take the alternate definition of the function to examine this limit. We know that that expression is bigger than or equal to 0. We also know that that expression is equal to x squared times the absolute value of y over x squared plus y squared, because every term in it is positive except for the y. That's the only one that could impact the sign of this. And so it's sufficient to just put the absolute value around that. Now we also know that x squared plus y squared has to be at least as big as x squared, because we're adding something on to x squared, which means that this expression is then less than the absolute value, or less than x squared times the absolute value of y over x squared, because we've replaced the denominator with something smaller than the denominator. Well, this expression is just the absolute value of y, because the x squareds cancel as long as we're not at 0, 0, which we're not when we're taking our limit, right? We're near 0, 0, but we're not at it. So what we have now is this string of inequalities. We've trapped our original expression between 0 and the absolute value of y. But we know that the limit as x approaches y, or of xy, as xy approaches 0, 0 of 0, that's 0. We also know that the limit as x approaches y, or of x as xy approaches 0, 0, I keep saying that wrong, of absolute value of y must be 0, which means by the squeeze theorem, which we've seen in one variable calculus, this limit, the limit as xy goes to 0, 0 of this middle expression must also equal 0. So this limit is 0 by the squeeze theorem, and we have successfully calculated it. So we just saw 3 limits that did exist, but now let's talk about when limits do not exist. So we've already seen that in 2 variables, the limit must be the same along every possible path. And so if 2 paths give different results, the limit doesn't exist. So that gives us something called the 2-path test to determine whether or not a limit does not exist. So the goal here is to find 2 paths. So to show a limit doesn't exist, we're going to approach along one path and then approach along a different path that we suspect might have a different limit. And if they don't match, then the limit does not exist. So it's really important to note that this test can be used to prove that a limit doesn't exist, but it cannot be used to prove it does exist. All right, let's start with an example here where we have the limit as xy approaches 0, 0 of the function xy over x squared plus y squared. And so we're going to examine this along 2 paths, the path y equals x and the path y equals 2x. So let's do path 1 first. If we approach along that path, then we're limiting our investigation to all the places where y equals x, which means our limit becomes x times x over x squared plus x squared, replacing all of our y's with x. So that's x squared over 2x squared. I should still have my limit in there. And simplifying that algebraically before we take the limit, we get the limit as xy approaches 0, 0 of 1/2, because the x squared cancels. As long as we're not dividing by 0, we can cancel those out. And so that limit is just 1/2. Let's compare that to path 2. Here, if we take the limit as xy approaches 0, 0, where y is twice as big as x, we're going to get x times 2x over x squared plus 2x squared. And so then we have the limit as xy approaches 0, 0 of 2x squared over x squared plus 4x squared, which is 5x squared. And we know then that we can cancel out those x squareds again, and we get 2/5, which is of course 2/5. So we found 2 paths along which we get 2 different values for the limit. So this limit does not exist. Again, we'll note that even if these 2 limits had matched, that would not be sufficient evidence that the limit itself existed. All right, wrapping up what we've seen here, a 2-variable limit has to be path independent. The precise definition for a limit uses distance in the plane, but in order to evaluate them, we saw that our limit laws resemble the same rules for single variable rules, and that our direct substitution works pretty frequently for continuous functions. We also saw the 2-path test, but decided that that can prove non-existence, but is not at all useful in proving the existence of a limit. We're going to continue to use these limits to next explore the idea of continuity. And then we're also going to connect our limits to the surface behavior and partial derivatives.